Okay, so the question reads, balance the following equation for the reaction in an acidic medium by the ion-electron method, and it gives us our reaction here, or the equation. First thing you want to notice is it's asking us to balance it by the ion-electron method, which means that we are going to have to balance the number of electrons that are within this reaction. It's not going to be as simple as it is in kind of like a basic chemistry where you just put coefficients in front and balance it like that. You have to actually balance the charges as well. Another thing to notice is that it says in the acidic medium, which means that we will have some sort of H plus ion present. If it were to say a basic medium, then you'd have to manipulate the equation so that it had OH minus ions present. But again, since we're in acidic, we are going to be expecting to have H plus ions. So the first thing I like to do is to determine what is being oxidized and what is being reduced. Something that is being oxidized is losing electrons, thus its overall charge is more positive, or is a higher positive value kind of situation, because it's losing electrons. Electrons makes things very negative. Something that is being reduced is something that is gaining electrons, and it's going to be decreasing in charge. So why don't we just dive right in, and maybe it'll make sense if you don't already understand oxidation and reduction. So first let's look here. The easy one is the Fe2 plus and the Fe3 plus. As you can see, as going from reactant to product, 2 plus, it's going from 2 plus to 3 plus, meaning that it is actually losing electrons, and by losing electrons, it's becoming more positive. That's the 3 plus. So that was a dead giveaway. We can say, boom, this one's being oxidized. Now, off of elimination, you can then determine that the MnO4 minus is being reduced. But why don't I show you so you understand? So let's figure out the charge of the oxygen here. The charge of the oxygen is a 4 minus. So now if we want the whole MnO4 to be a minus charge, the Mn has to be something that'll equal a negative 1. So if we say Mn is 3 plus, then the whole MnO4 is a minus charge, because if you take 4 minus plus a 3 plus, you get a minus 1. I hope that made sense to everybody. So now if we look at the Mn on the reactant side and we look at the Mn on the product side, you will see that Mn3 plus goes to Mn2 plus, so it's reduced, meaning that it gained electrons. It's becoming a more negative charge. It's becoming less positive. So this here is being reduced. Alright, now so next what you need to do is you need to separate what is being oxidized and what is being reduced to help you balance charges, electrons, all that good stuff. So I'm just going to write over here Fe2 plus is going to Fe3 plus, and I'm going to write over here that MnO4 minus goes to Mn2 plus. And again, I'm just keeping with kind of like what I was showing you here with what's being oxidized and what's being reduced. So let's start over here with the Fe2 plus and the Fe3 plus. First of all, we want to balance it overall, kind of going back to that basic chemistry. Fe and Fe, there's only one of each, so we're good there. However, our charges are not equal, so we need to balance that. Basically, so what we want is you can imagine like an equal sign in between here, and we want the charge on this side to equal the charge on that side. Charge on the reactant equals the charge on the product. So if I were to add one electron on my product side, the two sides would now be equal. So if you think about it, 3 plus and one negative is going to give you a 2 plus. So we're good. Let's move on to this side now. MnO4 minus to Mn2 plus. Basically, as you can see, the first big red flag, there's no oxygens on my product side, so I need to add them. In these kind of reactions, you can add waters, hydrogen ions, in some cases the OH ions, so that way both sides are balanced. So easy peasy, let's add water to this side, so we have some oxygens on this side. But wait, it's not balanced. You have 4 oxygens on this side and you only have 1 here. So we'll add a 4 in front of the water. Now almost everything's balanced, except wait, now we have hydrogens on our product side. So we need to add hydrogens on our reactant side. Okay, but wait, not everything is balanced. Our MNs are balanced, there's 1 of 1, 1 of each. Our oxygens are balanced, there's 4. However, there's 8 hydrogens, so easy, just add an 8 coefficient here. Alright, cool. Next, we need to look at our charges. Just like what we did over here where we added an electron. We need to make our reactant charges equal to the product charges. So, first thing we can look at, we have a minus charge here. And then we have a plus charge here. Now you might want to just say, oh, it's neutral, you know, plus and minus, they kind of cancel each other out. However, there's an 8 coefficient, meaning that there is an 8 plus charge here and a minus charge here. So if you add the 8 plus charge plus the minus, you get a 7 plus charge on this side. Okay, so I'll write 7 plus. Circle it. Oh, let's look at this side. Okay, water's neutral, no charge. Mn2 plus. So there's a 2 plus charge on this side total. So again, imagine the equal sign. You need your reactant and product charges to be equal. So if I were to add 5 electrons onto this side, onto the reactant, sorry, I'm just copying everything back down, except I am now adding 5 electrons to my reactant. If I were to add 5 electrons, so let's say we take that 7 plus charge, we plus it with a 5 minus, what are you going to get? You're going to get a 2 plus. So now, both sides are balanced with charges. Next thing you want to do is you want to look over here and be like, okay, the number of electrons is not equal to the number of electrons over here, so the number of electrons in the reaction that was being oxidized is not equal to the number of electrons that is being reduced. So easy. This is an easy solution. You're just going to multiply it by 5 to get you 5 electrons. So if we multiply this whole thing by 5, you'll get 5Fe2 plus is equal to, or goes to 5Fe3 plus 5 electrons. So it's just, you know, just multiplying across. And now we have the same 5 electrons in this one, 5 electrons in this one, which is important because it's going to allow you to cancel these out. You need electrons to be equal on both sides. So now what we're going to do is we're going to take this final one here, and we're going to take this final one here, and you're going to combine them into one equation. So combine. Alrighty. So I just would suggest being very careful. This is a place where a lot of people make mistakes. You don't always write all your reactions, you don't always write all your products, and you don't always cancel the right things. So just be careful. So let's start over here. Let's write my reactants. 5Fe2 plus. That's all my reactants. Let's write my reactants over here. 5 electrons plus 8H plus MnO4 minus. And then we're going to write our products. So 5Fe3 plus 5 electrons plus Mn2 plus, we're going over here, plus 4H2O. Alrighty, so next we can look at things that can be canceled. We have 5 electrons in our reactants. We have 5 electrons in our products. We can cancel them. Awesome. Is there anything else we can cancel? No. You might look and go, oh, I could cancel the Fe here and the Fe here. But you can't. Fe2 plus is on the reaction side and Fe3 plus is on the product. So they're not technically the same thing and thus can't be canceled. So now I'm just going to take everything here and condense it now, taking out the 5 electrons. So 5Fe2 plus 8H plus MnO4 minus goes to 5Fe3 plus plus Mn2 plus 4H2O. And so, if you look at it, this is your final balanced equation. And if you were to check it, your charges on your reactant side should equal the charges on your product side.